Now, while most of the focus so far in this unit has been on the art side and the religion side of things, we want to conclude the Renaissance when we look at the scientific Reformation or the scientific revolution that occurred from this. And so the first thing we're going to do is we're going to really start off with placement. Like where do we exist in this whole grand scheme of the universe? And really, what we find here is the idea that up until the mid-1500s, scholars accepted that what the Greeks believed, that the universe was geocentric, meaning that the Earth, us, sat right here in the middle of the solar system. And the sun and the moon and everything else revolved around us. And so that's really the idea. Like that's you can see that in the literature leading up to that time, and the idea, even in today's sun, the idea that the sun sets, that we believe, even in our vernacular, the way that we talk, that the sun rises and sets. When in reality, the sun's, like, relative to us, it's not moving. It's us that's really rising and setting for the sun. So Nicholas Copernicus comes along in 1543, and he writes a work of science called On the Revolutions of the Heavenly Spheres. And he proposes the heliocentric model, the sun-centered model, that our solar system revolves around the sun. And then that's taken a little bit further by a Danish astronomer by the name of Tycho Brahe in the late 1500s. So we're now beginning to get this idea of a collection of scientists that are all just coming together and saying, yeah, you know, really it makes more sense that this giant glowing ball is what we're revolving around, okay, that it moves, that we move around it. And then Johannes Kepler, Brahe's assistant, further reinforces the heliocentric model, but then he adds the concept of elliptical orbit. So as you can see in this image here, we assume that it's all circular. You know, it's just like this straight, perfect circle. But Brahe Kepler comes along and says, no, it's really more of an elliptical type thing. So it's oval-like. It's more oval, and so it's not a consistent thing, which explains seasonal changes, which explains the fact that there are movements of the location of the sky. It's not this perfect, always in the same place circle. And then we have Galileo Galilei. Yes, it's the guy who's mentioned in Bohemian Rhapsody. Galileo, that thing. He comes up with a telescope, and he supports his findings. When you're able to look deep into the darkest depths of space, you're able to look out there and say, yep, heliocentric. We are definitely revolving around the sun, not the other way around. He develops practical data. And so we're seeing here that instead of it just being all these like really, really educated guesses, we're actually finding evidence, scientific evidence to put this stuff up there. He then, by putting this stuff out there, gets the ire of the Spanish church. They try him, and he is spending the rest of his life under house arrest, stuck at home. So imagine quarantine forever. That's kind of what happens to Galileo Galilei. Now, as we move on from the scientific revolution, we're going to have to talk about the thing that still affects your science today. Whether you have taken biology or chemistry or earth sciences or physics or whatever it is that you're into, chemistry, you've got to use the scientific method. And the scientific method is a pretty basic concept, as you can see it here. It's a step-by-step process used to confirm findings, and you say that you either prove or disprove your hypothesis. Rather, really, I think the better way of putting it would be you support or disprove your hypothesis. So you don't really prove anything. Science is always moving forward. You always get to go things, you know, that theoretically, you know, gravity is not proven. I could drop this thing right here, and you know, theoretically, at one point I could drop it and it's going to go up instead of down. So again, there's that idea that there's always some aberration to it, but you support that hypothesis. This idea comes to us via Francis Bacon, who was a philosopher. He was a philosopher, artist, and really kind of his own Renaissance man. He doesn't get the same credit that we give to like Leonardo and Michelangelo, but he's definitely one of them. So he believes in experimentation and observation. So this is where the scientific method really comes into play. We've got observation and question. So if I'm going to do scientific method, I'm going to watch things, and I'm going to look around and go, okay, well, why does this happen? Or why does this work the way that it does? Then I begin to do some research and I find out what is the existing information about that particular question that I have. Then I can form a hypothesis. And then I do an experiment to test that hypothesis. So I'm putting my prediction to the test by actually doing it. I collect the data, and then I analyze that data. And then I form a conclusion. And then it's not on here, but in modern times especially, once you form that conclusion, once you've got that data, you still need to publish what it is. So if I have a theory that 9 times out of 10 when I drop this, it will bounce to the right. Okay, so I drop it 9 times and it bounces, it hits the ground and it bounces to the right. That's actually your left, but it's my right, so whatever. Okay, so it bounces that way, 9 times out of 10. Okay, so I do that experiment and it does. It bounces to the right 9 times out of 10. So I analyze, why did it happen? What did I do? What was going on? My conclusion is my hypothesis is supported. Okay, move on. Now, in true scientific method, one test is not enough. I need to replicate that test exactly a number of times in order to create more validity to my hypothesis. Okay, so I continue to do that. But I need to tell people, hey, I did this experiment and this is what happened. 9 times out of 10, verified or supported my hypothesis. But if my hypothesis is disproven, I drop it and 6 times it goes left and 3 times it goes right, or four times it goes right. I still need to report, hey, this is my hypothesis and it was disproven. It wasn't upheld. And so it changes. Philosopher type within the same sort of thing is the idea of Rene Descartes. Rene Descartes makes the argument of I think, therefore I am. In other words, I exist because I am capable of thinking. I'm capable of having independent thought. And both of these guys, Bacon and Descartes, say the physical world cannot fit within the teachings of the church at the time, what they were saying. There are definitely things that science seems to stand outside of what's being taught and preached in the church. Both believe really that truth is found via a long process of investigation. It means that, really we're not gonna just know right off the bat. We're gonna have to go through the process. And again, like I said, I can do this 9 times out of 10 and it's going to confirm it, but that's just one iteration of it. I need to do it multiple times to prove, and it's going to take me a long time to prove what's happening. So the argument that people have of, well, it worked for me is not scientifically valid, simply because working for you in one situation is not proof that it works in all situations, or even most. A hypothesis, the definition really of that is that it is a logical explanation. Sometimes I hear it referred to as it's an educated guess, which really still, I think, it falls into the same category. I mean, it makes sense and there's some basis behind it. All right, last thing we're going to talk about in this unit, and really the last notes that we're going to have for the semester before we start diving into project work. Medicine and chemistry. Andreas Vesalius in 1543 wrote and drew something called On the Structure of the Human Body to give us a greater understanding of the human anatomy. So if you Google Vesalius, you're going to see a lot of these pictures here, which are essentially human beings, drawings of human beings, musculature with no skin. So you can see where the muscles are and how things are made. There's an interesting, I think it's in China, where there is an actual living exhibit, not living exhibit, but an actual exhibit where they have taken cadavers, human cadavers, and done this in real time. Like that's an actual human being where the skin has been removed and you can see the musculature. It's pretty controversial, as was Vesalius's sort of drawings way back when. The microscope is invented during this time. That's it, right there. That's what the earliest microscopes look like. Very, very basic, and obviously magnification, nothing like we have today. Robert Boyle is a chemist, and he comes up with Boyle's law, which you can see here. So one of those significant things, if you're in chemistry and you haven't heard of Boyle's law, you will pretty soon. It's a thing. And then you've got in Isaac Newton, gravity and calculus. In 1687, he wrote Mathematical Principles of Natural Philosophy. And then famously, he sat under a tree and an apple allegedly hit him on the head. And he said, "Ooh, gravity." But the basic idea is that he was able to observe the natural world, form a hypothesis, test it, and now we have the law of gravity. That no matter how many times I drop this, it's going to always land on the ground. Unless there's an aberration somewhere in science and it goes up. That's it for the first semester. So when we come back, it's going to seem really long. Right? It's going to be like a month before we do new notes on this particular stuff. But when you guys come back in 2021, fingers crossed, we will begin starting the Age of Exploration. So we're going to be looking at how explorers begin to discover new paths, new trade routes, the new world, as well as colonization, and how that impacts the global structure of things. So that's it for now. Hope you guys enjoyed this. I'm sure we'll see each other via Zooms and this kind of, I may pop up again on a few things here and there. But if not, at the very least, hope everything goes well for the holidays.